Hello, everyone. I hope you are feeling settled and ready to unwind. Take a deep breath in, hold it for a moment, and slowly let it go. Allow your shoulders to drop, your jaw to relax, and let the weight of the day simply drift away. As your body finds stillness, let your mind open to the vastness above us. Today, we will explore stars. When we look up at the night sky, past the clouds and the glow of our cities, we see thousands of tiny, flickering points of light. They seem quiet, distant, and unchanging. They have guided sailors across oceans and inspired storytellers for millennia. Yet, these delicate pinpricks of light are in reality immense, powerful engines of energy, scattered across the cosmos in numbers we cannot truly comprehend. A star is not merely a shining object. It is a profound balance of forces, a sphere of glowing plasma held together by its own immense gravity. At their core, stars are the universe's furnaces. They are enormous balls composed mostly of hydrogen and helium, the simplest and most abundant elements in existence. But a star is more than just a cloud of gas. It is defined by what happens deep inside its heart. In the center of a star, the pressure and temperature are so intense that atoms are forced together, fusing into heavier elements. This process, nuclear fusion, releases unimaginable amounts of energy. It is this energy, fighting its way outward from the core, that makes a star shine. It travels for thousands, sometimes millions of years through the star's layers before finally escaping the surface as light and heat, traveling across the vacuum of space to eventually reach our eyes. Every star you see is a delicate equilibrium. Gravity, the same force that keeps our feet on the ground, is constantly trying to pull the star's immense mass inward. Without an opposing force, the star would crush itself into oblivion. That opposing force is the energy generated in the core. This outward pressure pushes back against gravity, holding the star stable, sometimes for billions of years. This silent, colossal tug-of-war is what maintains the shape and stability of every star in the universe. Our sun, which seems so normal to us, is more than 100 times wider than Earth and over 300,000 times more massive. Yet our sun is merely an average star. There are dwarf stars barely larger than Jupiter, glowing dimly red. And then there are supergiants, colossal behemoths so vast that if placed in the center of our solar system, they would swallow up Earth, Mars, and even Jupiter inside their fiery atmospheres. Before a star begins to shine, there is only coldness and darkness. The space between existing stars is not truly empty. It is filled with vast, tenuous clouds of gas and fine dust known as nebulae. These are the stellar nurseries, the cosmic wombs where stars are born. These clouds can stretch for hundreds of light years, composed mostly of hydrogen atoms floating silently in the frigid vacuum. For eons, these clouds may drift undisturbed, dark silhouettes against the background glow of the galaxy. The birth of a star begins not with a bang, but with a slow, almost imperceptible shift. Gravity is a patient sculptor. Within these vast clouds, some regions are slightly denser than others. Perhaps a nearby supernova sends a shockwave through the cloud, or perhaps the slow rotation of the galaxy causes material to clump together. Whatever the trigger, gravity begins its work in these denser pockets. Atom by atom, dust grain by dust grain, material is pulled inward. As the pocket grows in mass, its gravitational pull becomes stronger, drawing in even more surrounding gas. Imagine a vast region of space slowly collapsing onto itself. As the gas falls inward, it begins to rotate. Conservation of angular momentum causes the shrinking cloud to spin more rapidly. This rotation flattens the cloud into a spinning disk, with a dense core forming at the center. This central core is the protostar, an embryonic star not yet fully formed. Deep within this protostar, conditions are changing drastically. As gravity continues to crush the material together, the gas particles collide more frequently and with greater speed. These collisions generate heat. The cold interstellar cloud transforms into a warm, glowing object shrouded in a thick cocoon of dust that hides it from our view. The protostar continues to grow, feeding on the surrounding disk of gas, growing hotter and denser with each passing millennium. This process can continue for millions of years. The protostar is not yet a true star because it is not yet sustained by nuclear fusion. It shines only with the heat generated by its own gravitational collapse. It is waiting for a critical threshold to be crossed. The temperature in the core must reach millions of degrees. Only then will the hydrogen nuclei move fast enough to overcome their natural repulsion and slam together. Once that temperature is reached, ignition occurs. In the deep, crushing pressure of the core, hydrogen atoms fuse to create helium. A spark is lit that will burn for billions of years. The star stabilizes. A star is born, ready to begin its long life on the cosmic stage. Once a star has ignited nuclear fusion in its core, it enters the longest and most stable period of its life. Astronomers call this phase the main sequence. It is the adulthood of a star, a time of balance and steady output. Our own Sun is currently in the middle of its main sequence phase, a period that has already lasted upwards of 4.5 billion years and will continue for billions more. During this time, the star is in a state of profound equilibrium. It is a perfect standoff between two colossal forces. Inwardly, gravity relentlessly tries to pull the star's immense mass towards its center. Outwardly, the tremendous pressure generated by the energy of nuclear fusion pushes back. As long as the star has hydrogen fuel in its core, this balance is maintained. The star shines steadily, its size and temperature remaining relatively constant over vast stretches of time. The duration of this stable phase depends almost entirely on the star's mass. It is a counterintuitive truth. The more massive a star is, the shorter its life. One might assume that a larger star with more fuel would burn longer, but the opposite is true. Massive stars have immense gravity pressing down on their cores. To counteract this crushing weight, they must fuse hydrogen furiously, burning through their vast reserves at a prodigious rate. A star 10 times the mass of the Sun might burn for only a few tens of millions of years, a brief spark in cosmic time. Conversely, stars with less mass than the Sun have less gravity to contend with. Their cores are cooler, and they fuse hydrogen much more leisurely. A small red dwarf star sips at its fuel so slowly that it can remain on the main sequence for trillions of years. These tiny, dim stars will be the last lights shining in the cosmos, long after giants like our Sun have faded away. Our Sun sits comfortably in the middle of these extremes. It is a yellow dwarf star, burning its fuel at a moderate pace. This stability is crucial for us. The steady, unwavering light and heat provided by the Sun have allowed the complex processes of life to evolve on Earth. While on the main sequence, a star's appearance is defined by its surface temperature. Hotter stars appear blue or white, while cooler stars appear orange or red. For billions of years, a star does little more than shine, maintaining its delicate balance and acting as a gravitational anchor for its planets. It is a quiet, steady burn, the long, enduring act of a star's life. When we look at the stars, they might all seem like similar white dots, perhaps varying only in brightness. But if you look closely, or if you look through a telescope, you will see that stars come in distinct colors. These colors are not just for show. They are direct indicators of a star's surface temperature, which in turn tells us about its mass and its life story. Astronomers classify stars based on their spectrum, the rainbow of light they emit. The classification system uses a sequence of letters O, B, A, F, G, K, and M. At one end of the scale are the O-type stars. These are the giants of the stellar world. They are incredibly hot, shining with a brilliant, intense blue light. They are massive, rare, and short-lived, burning through their fuel with ferocious intensity. Moving down the sequence, we find the A-type stars, which are white or blue-white. Sirius, the brightest star in our night sky, is a prime example. Further along, we reach the yellow-white and yellow stars, like our own Sun, a G-type star. These stars are moderately hot, common, stable, and they live for billions of years. Finally, at the cool end of the spectrum are the M-type stars. These are the red stars. Their surface temperatures are relatively low, shining with a soft, ruddy glow. While they appear dim to our eyes, M-type stars are actually the most common stars in the universe. Understanding these types helps us read the night sky, seeing not just points of light, but a diverse population of objects, each at a different stage of a grand cosmic cycle. Let us turn our attention now to the quietest, most numerous, and longest-lived inhabitants of our galaxy, the red dwarfs. These are the M-type stars, the introverts of the stellar neighborhood. They are so dim that not a single red dwarf is visible to the naked eye from Earth, yet they make up perhaps 70% of all the stars in the Milky Way. A red dwarf is a star with only a fraction of the Sun's mass. Because they have such low mass, the pressures and temperatures in their cores are just barely high enough to maintain fusion. They burn their hydrogen fuel incredibly slowly, sipping at it rather than gulping it down. This slow burn leads to phenomenal longevity. while a massive star might live for a few million years, and our Sun for about 10 billion, a small red dwarf can remain shining for trillions of years. Every single red dwarf that has ever been born since the dawn of time is still shining today. They are the eternal watchers of the cosmos. Unlike larger stars, red dwarfs are thought to be fully convective. The plasma inside them circulates constantly, like boiling water in a pot. This constant mixing ensures that the entire star's supply of hydrogen is eventually used for fusion. In the incredibly distant future, long after the sun has died and the bright, massive stars have burnt out, the universe will belong to the red dwarfs. They will continue to glow with their soft, ruddy light, slowly cooling over eons, the final glowing embers of a once brilliant cosmos. What fate awaits a star like our own sun? For billions of years, a sun-like star maintains a delicate balance, but eventually, the hydrogen in the core runs out. The fuel gauge hits empty. When this happens, the fusion engine that supported the star's immense weight sputters and stops. Without the outward pressure, gravity instantly takes over. The helium-rich core begins to collapse inward, getting hotter and hotter. This intense heat radiates outward into the layers of gas surrounding the core. The hydrogen in these outer layers ignites, burning furiously. This causes the star's outer layers to expand dramatically. The star swells up to many times its original size. As it expands, it cools down, shifting color to a deep, glowing orange-red. The star has become a red giant. When our sun becomes a red giant in about 5 billion years, it will swell so large that it will likely engulf the inner planets. The horizon will be filled by a colossal, ruddy sun. Deep in the core, a new type of fusion begins, helium fusion. The star finds a temporary new stability, but this phase is relatively short-lived. Eventually, the star will puff its outer atmosphere away, creating a beautiful, glowing shell of gas called a planetary nebula. At the center, the bare, super-hot core is left exposed, an incredibly dense, hot object called a white dwarf. Slowly cooling over billions of years, a silent monument to a star that once shone brightly. While sun-like stars face a gentle decline, the lives of massive stars are far more dramatic. We are talking about stars 8, 10, or 20 times the mass of our sun. These are the rock stars of the cosmos. They live fast, burn brightly, and die young in spectacular fashion. Their immense gravity demands a furious rate of fusion just to keep them stable. They shine with searing blue or white light, pumping out enormous amounts of radiation. Inside these massive stars, the fusion process doesn't stop at carbon and oxygen. When a massive star exhausts its hydrogen, it becomes a supergiant, swelling to incredible proportions. Its core contracts and heats up, fusing helium into carbon. When helium runs out, the core shrinks again, getting even hotter until it can fuse carbon into neon and magnesium. This process repeats like a cosmic nesting doll. As each fuel runs out, the core collapses and ignites the ash from the previous stage. Neon fuses into oxygen, oxygen fuses into silicon and sulfur. The star becomes layered like an onion, with different fusion reactions occurring in shells around the center. The final stages happen with frightening speed. Silicon fusion, the very last step, might last only a few days. In these final moments, the star is frantically forging heavier elements in a desperate attempt to withstand its own crushing gravity. The end of the road for fusion is iron. Iron is a special element. Fusing iron doesn't release energy, it consumes it. Once the core transforms into solid iron, the fusion engine hits a brick wall. In a fraction of a second, gravity wins. The collapse of a massive star's iron core is incredibly violent. Imagine the mass of our sun being crushed into the size of a city in less than a second. The outer layers of the star, rushing inward, suddenly hit this unimaginably dense ball at the center. They bounce off with tremendous force. This is a core collapse supernova. For a few weeks, this single exploding star can outshine an entire galaxy of hundreds of billions of stars. The amount of energy released in a few seconds is more than our sun will radiate in its entire lifetime. But this explosion is not just a destructive force, it is a supreme act of creation. During the intense heat and pressure of the shock wave, a rapid-fire series of nuclear reactions occurs. This process forges elements even heavier than iron. Elements like gold, silver, and uranium. Almost all the elements in the universe heavier than iron were created in these fiery crucibles. The explosion hurtles this material out into the galaxy at thousands of kilometers per second. This is the cosmic recycling system. The death of one massive star provides the raw materials for the next generation of planets and life. The carbon in your cells, the iron in your blood, the gold in your jewelry, it was all blasted into space by supernovae long before our solar system existed. We are intimately connected to these violent events. Without them, the universe would be incapable of forming rocky planets or complex life. A supernova is a spectacular end, but also a necessary beginning. What is left behind after the titanic explosion of a supernova? The outer layers are gone, but the core, that incredibly dense sphere, remains. If the star was large but not the largest, the core becomes a neutron star. During the collapse, electrons and protons are squeezed together to form neutrons. The result is a sphere made almost entirely of neutrons, packed together as tightly as the nucleus of an atom. A neutron star is an object of mind-bending extremes. It packs a mass greater than our sun into a sphere only about 20 kilometers across. Imagine a city containing an entire star. The density is incomprehensible. A sugar cube-sized amount of neutron star material would weigh about as much as a large mountain on Earth. The gravity on the surface is billions of times stronger than what we feel here. As these cores collapse, they spin up. Some rotate hundreds of times every single second. They also possess intense magnetic fields, trillions of times stronger than Earth's. Sometimes these fields funnel beams of radiation out from their poles. As the star spins, these beams sweep across the sky like the light from a lighthouse. When we detect these regular rhythmic pulses, we call them pulsars. They are the most precise clocks in the universe, spinning silently in the dark, holding on to the energy of their former lives in an incredibly condensed, extreme form. Sometimes gravity wins completely. If the star that explodes as a supernova is truly massive, the collapsing core is too heavy even for neutrons to support. The inward crushing force of gravity becomes unstoppable. The core shrinks smaller and denser, smaller and denser. The gravity becomes so intense that the escape velocity, the speed needed to break free, exceeds the speed of light. Since nothing can travel faster than light, nothing, not even light itself, can escape. The object vanishes from the visible universe, leaving behind a dark region where gravity reigns supreme. A black hole is born. At the very center lies a singularity, a point of infinite density. Surrounding this point is the event horizon, the point of no return. It is not a physical surface, but a boundary in space. Once anything crosses the event horizon, it is forever trapped, destined to fall inward toward the center. Stellar mass black holes may be only 10 to 100 kilometers across, yet they contain the mass of several suns. Because they emit no light, we find them by watching their influence on the space around them. We see gas spiraling inward, heating up to millions of degrees before it disappears forever. We see stars orbiting an invisible point in the dark. Black holes are the ultimate triumph of gravity over matter. They are regions where space and time itself are warped to the breaking point, the final, complete end of a massive star's journey. When we look at the sky, we tend to think of stars as solitary individuals, like our sun. But our sun is somewhat unusual in being alone. The majority of stars in the galaxy are social creatures. They are born together and they live together. Many stars exist in binary systems, where two stars orbit around a common center of gravity. They can be close together, whirling around each other in a matter of days, or far apart, taking centuries to complete a slow, graceful waltz. Stars are also born in groups. When a giant nebula collapses, it doesn't just form one star, it forms hundreds or thousands at the same time. These groups are called star clusters. The first are open clusters. These are young, loose groupings of stars. The famous Pleiades, or Seven Sisters, is a beautiful example. Like siblings leaving home, these stars will eventually drift away to live solitary lives. The second type are globular clusters. These are immense, tight spherical swarms containing millions of stars packed into a small volume. These clusters are ancient. They are some of the oldest structures in the universe, formed when the galaxy was just beginning to take shape nearly 13 billion years ago. They orbit in the halo of the galaxy, like bees swarming around a hive, gravitational fossils holding the history of the early universe within their dense cores. When we look up at the constellations, we see shapes that have remained unchanged for thousands of years. The Big Dipper, Orion, and Cassiopeia seem like permanent landmarks, frozen in the dark velvet of the night. Because our lives are so short, we perceive the stars as fixed points of light, but this stillness is an illusion. In reality, every star you see is moving through space at incredible, mind-bending speeds. They are part of a grand, silent migration across the galaxy. Imagine the Milky Way as a vast, swirling whirlpool. Every star is a tiny droplet caught in the invisible current of gravity. Our own sun is traveling at about 720,000 kilometers per hour. Even at this frantic pace, the galaxy is so immense that it takes us 230 million years to complete just one single orbit around the center. The reason the stars appear stationary is simply the sheer, staggering distance between them. If you could record the sky and play it back in a time-lapse spanning thousands of years, you would see the constellations slowly warping and dissolving. The stars of the Big Dipper would drift apart. The belt of Orion would loosen and fade. As you lie there, consider the quiet journey we are on. We are not sitting still on a stationary planet. We are passengers on a rocky sphere which is orbiting a star which is itself rushing through a vast, dark ocean of space. Every star you see is a fellow traveler, each on its own unique trajectory, guided by the patient hand of gravity. There is a deep, rhythmic peace in this motion. It is a movement so vast and so smooth that we cannot feel it, yet it connects us to the dynamic flow of the entire cosmos. Light is the only bridge we have to the stars. Since we cannot travel to them, we must learn to read the messages hidden within the light they send us. One of the most beautiful aspects of this message is color. If you look carefully at the night sky, you will notice that the stars are not all the same shade of white. Some have a distinct sapphire blue tint, others glow with a warm campfire orange, and some shine with a deep, somber red. These colors are a direct map of temperature. A piece of iron in a blacksmith's forge first glows a dull red, then a bright orange, and if it becomes hot enough, a brilliant white blue. Stars follow this same rule of physics. But there is a curious mystery. Why are there no green stars? Even though green sits in the middle of the spectrum, no star appears green to our eyes. The reason lies in how our eyes perceive light. A star that peaks in green is actually emitting a huge amount of all the other colors as well. When our eyes receive this mixture, our brain processes it as pure, clean white. Green is hidden in the balance, masked by the presence of the other colors. The colors of the stars also tell us about their age. Blue stars are the youth of the galaxy, hot, vibrant, and burning with passion. Red stars are often either the very old, which have swollen and cooled, or the very small and patient. As you close your eyes, imagine the sky as a vast celestial palette. It is a gallery of light, painted with the heat of billions of suns. Everything is balanced, everything is blended, and everything is glowing in its own perfect time. We often think of space as a place of absolute silence, and while it is true that sound cannot travel through the void, stars themselves are not quiet. Stars are constantly vibrating, ringing like giant celestial bells. Deep inside a star, there is a chaotic symphony of motion. Vast currents of hot plasma rise to the surface, cool down, and sink back again. This movement creates pressure waves, sound waves, that travel through the star. As these waves bounce around inside, they cause the star to pulse, to expand and contract in complex rhythmic patterns. Every star has its own unique song. A massive giant star vibrates slowly with a deep, low-frequency hum. A smaller, denser dwarf star vibrates with a higher, faster frequency. By measuring these tiny changes in brightness, astronomers can hear what is happening deep inside the star. These vibrations reveal things that light alone cannot. They show us the heartbeats of the stars, steady, pulsing rhythms that can last for minutes or days. Some stars vibrate with many frequencies at once, creating a complex, harmonious chord that echoes through their layers. Tonight, imagine the universe as a vast, silent orchestra. Though our ears cannot hear them, the stars are all humming. Each one is singing its own part in a grand symphony. There is a profound comfort in this idea that the light we see is accompanied by a silent, rhythmic pulse. Everything is in motion, everything is vibrating, and everything is part of the same grand, peaceful song. Let us travel back, far beyond the stars we see tonight, to a time when the universe was completely dark. For hundreds of millions of years after the Big Bang, there was no starlight. The cosmos was a vast, silent ocean of cold hydrogen and helium gas. Astronomers call this the cosmic dark ages. But in the deep shadows, gravity was working. Slowly, patiently, it pulled the primordial gas into massive clouds. Inside these clouds, the very first stars were beginning to form. These are the population 3 stars, the pioneers of light. These first stars were unlike anything that exists today. Because they were made of pure, pristine gas, they could grow to be hundreds of times more massive than our sun. They were enormous, incredibly hot, and shone with a fierce, brilliant blue-white light. They were the ones who finally ended the long darkness, illuminating the universe for the very first time. Their lives were brief, lasting only a few million years, but in that short time, they transformed the cosmos. Their intense radiation cleared the cosmic fog, and when they died in spectacular explosions, they released the first heavy elements into space. They planted the seeds for everything that followed. Though they are long gone, their legacy is written in the light of every star that followed. They were the ancient ancestors of our galaxy, the lonely giants who first woke the universe from its long sleep. While many stars shine with a steady, unwavering light, some stars seem to breathe. These are the variable stars. Their brightness is not constant. It rises and falls in a rhythmic, predictable pattern, like a slow, celestial heartbeat. Imagine a star that physically expands and contracts. As it grows larger, it cools and dims. As gravity pulls it back in, it compresses, heats up, and brightens. This cycle can take days, months, or even years. To astronomers, these breathing stars are more than just a curiosity. One special type, called Cepheid variables, acts as the universe's gold standard for measuring distance. The speed of their pulse is directly linked to how truly bright they are. By watching how fast a star breathes, we can calculate exactly how far away it is, even if it is in a distant galaxy millions of light years away. They were the key to discovering that our universe is much larger than we ever imagined. There is a quiet beauty in the idea of a pulsing star. In the deep silence of space, these stars are keeping time, acting as lighthouses that guide us across the vast distances between galaxies. When you look up, remember that the sky is not a static image. It is a living, pulsing environment filled with stars that are constantly changing, breathing, and lighting the way for us to understand the scale of the infinite. A star is more than just an engine of energy. It is an anchor. It is the center of a family, holding a collection of planets, moons, and asteroids in its warm gravitational embrace. Gravity is the invisible thread that ties a planet to its star. Without this connection, worlds would drift aimlessly through the cold, dark vacuum of space. But a star provides a hearth, a source of light and heat around which a planetary system can thrive. Every star has what we call a habitable zone, or the Goldilocks zone. It is the region where it is not too hot and not too cold. It is the perfect distance where liquid water can exist on a planet's surface. Our Earth sits perfectly within this delicate band, nurtured by the steady glow of our sun for billions of years. But stars are also protective. As a star moves through the galaxy, it creates a massive bubble in space, pushed out by the stellar wind. This bubble protects its planets from the harsh cosmic rays of deep space, acting like a shield for the fragile life that might be growing on worlds like ours. When we look at a star, we are looking at the potential for a home. We now know that most stars in the sky have planets orbiting them. There are billions of worlds, each tied to its own sun, each one experiencing its own seasons, its own dawns, and its own quiet nights. The connection between a star and its planets is one of the most fundamental relationships in the universe. It is a bond of gravity, light, and protection, a silent promise that wherever there is a star, there is a chance for a world to call home. As we draw this journey to a close, let us reflect on what stars truly are. They are not just distant lights, they are the engines of the cosmos. Through their lives, they fight a constant battle against gravity, balancing incredible forces to maintain stability. But more importantly, stars are the creators. The carbon in your cells, the oxygen you breathe, the iron in your blood. It all came from the belly of a star that lived and died long before our solar system was born. We are chemically connected to the cosmos. As the saying goes, we are made of star stuff. When you look up at the night sky, you are looking at your ancestors. You are seeing the processes that made your existence possible. So now, as the night deepens, let the image of these slow-burning cosmic fires fill your mind. Think of the steady rhythm of a star, balancing gravity and energy for billions of years. Allow yourself to drift within this vast, quiet tapestry. There is nothing you need to do now. The stars are turning above, the universe is unfolding in its slow way, and you are a part of it all, safe, settled, and home. Thank you for spending this time exploring the stars with me. Let your breathing slow, let your thoughts settle, and rest peacefully. Good night.